Let's now take a look at a scenario where we want to do a confidence interval for the mean. However, the population variance is actually unknown, which is really a more realistic scenario. It's very rare that we'd actually know sigma to begin with. Just like in the previous example, the data types applicable are interval or ratio. And this scenario is the exact same scenario and the same data that we just worked with. Again, we want to estimate with 95% certainty the true average time it takes for this pain reliever to kick in and do its thing. The only thing difference in this write-up from the previous was that there's nothing here about sigma, because we don't know what sigma is. Okay, let's talk about this a little bit. What's going on here? Now, it's very, very seldom, if ever, that we actually know the value of sigma. It just doesn't happen. If you know sigma, then realistically you should already know mu. Look at the calculation here for sigma. Sigma squared equals the sum. And whoops, there's a typo here. I'm going to fix that real quick through the magic of technology. That's I equals 1 to capital N, the sample size, of xi, the individual observations, minus mu, the true mean, squared divided by n. This is what sigma squared is. Square root of this is simply sigma. Well, look what's right in the middle of this calculation, mu. We're trying to estimate mu. Well, if you have sigma, you already calculated sigma, then you must have mu. So why are you trying to estimate mu if you have mu? So it doesn't make a lot of sense. It's very rare that we have a value for sigma without having mu. Okay, so the confidence interval should look like this. It should have the form x bar plus or minus z of alpha over 2. We don't have sigma. Our best estimate for sigma is f, the sample standard deviation, divided by square root of n. See, if I had sigma up here, this would be the z interval that we've been doing. However, this is actually not accurate. Thanks to Beer and a guy named Gossett in England, 1876 to 1936, Gossett worked for the Guinness Brewery. And during the process of various quality control and testing stuff of the beer, he realized that the standard normal distribution, z, was not appropriate when estimating the mean when we had a small sample size and an unknown value for sigma. The combination. If we have larger sample sizes, then the unknown value of sigma was not as significant. It's not that big of a deal. But on a small sample size, and we don't know sigma, we use S to estimate sigma, he realized it was wrong. The probabilities were not really matching up. The distribution will be that of a t distribution and not a z distribution. So here's a new distribution we introduced to you, the t distribution. It's actually come from the student t distribution. Gossett wrote under the pen name of student because back then, and actually it's probably true today too, when you work for a company and as part of your work you discover something that tends to belong to the company, Gossett wanted this knowledge. He realized how important it was, so he wanted everybody to have it, so he wrote under this pen name so that the brewery wouldn't realize that he was giving away their secrets. Okay, the characteristic of the t distribution. First of all, it's bell-shaped. When you draw a t distribution, it looks just like a normal distribution. If I draw a bell curve, you couldn't tell me whether that was a normal distribution or if it was a t distribution. However, if this is a normal distribution and I draw a t distribution over top of it, that's when you start to see it. What happens is the tails are actually heavier in the t distribution. So there's more probability out here in the tails. Now this still goes, I didn't do a real good job of drawing this, these tails still go down asymptotically to 0. But because the tails are heavier, there's more probability out in the tails for a t distribution with a small sample size than there is for a z distribution. And actually what happens is, as the sample size increases, if this is my normal distribution, as the sample size increases, the t distribution gets closer and closer and closer, to a, didn't want that. Oh, the wonders of technology. Yeah, let me start that whole thing over. Here's my normal curve. as the sample size gets bigger, this curve gets closer and closer and closer. The t curve gets closer and closer to the z distribution. At a certain point, in terms of probabilities, there's not much difference between them at all. What's that certain point? Roughly n equals 30. The CLT applies. The t distribution is actually a family of curves, where each curve is defined by what's known as the degrees of freedom. Now, on this level of course, we're not going to get into a deep discussion at all about what degrees of freedom are. Numerically, the degrees of freedom is simply the sample size less 1. So n minus 1 is the sample size. We've seen the degrees of freedom before. When we calculate the sample standard deviation, we divide it by n minus 1. We're actually dividing by the degrees of freedom. So as n gets bigger and bigger and bigger, as n gets huge, the t curve will converge and look just like the standard normal curve. You won't be able to tell the difference between them. Now, as the sample size increases, the t distribution, actually I just said this, converges to the z distribution. And we see this happening at approximately n equals 30. Now, our confidence interval for the mean, when the population standard deviation is then unknown, will now have the form of x bar plus or minus t on the appropriate degrees of freedom, still alpha over 2, s over the square root of n. This degrees of freedom, don't freak out by this down here. This is just simply stating which t distribution we're using. We didn't need this degrees of freedom when we were talking about the standard normal, because there's only one standard normal. All we needed was the alpha over 2. But the t curve will actually change based on the sample size. So the degrees of freedom is actually the sample size minus 1. So that's telling us which t to use. So this is what our confidence interval is going to actually look like. Now the assumptions is that data was sampled from a normally distributed population. That's our assumption. You can say x is distributed normal. Talking about x bar, ultimately the averages. Okay, well, if the data is distributed normal, or if the population is normal, we take a sample from it, the samples will also be normal. Now, the best way to make this determination is to look at what's known as a normal plot. A normal plot is simply a graphical representation of your data in such a way that we can look at it and say, hey, this looks normal. It's probably normal. Now, it's not a box plot. It's not a histogram. The problem with the histogram, if you recall, if I start changing the class widths, I can start changing the shape of the histogram a little bit. So that's not where we're going. The normal plot is something different. And I'll show you what that is in just a minute. Now, if the sample is, I'm going to say, approximately normal, and the sample is representative of the population, then the population must also be approximately normal. So this is the way we're going to actually determine with a small sample case when we have n less than 30. That's how we will determine if it's reasonable to assume that the population is normal. We take a look at a normal plot. If the data looks normal, then the population the data was taken from is probably also normal. Now again, if the sample size is large enough, approximately 30 or more, then we'll say the CLT applies, and we're not going to be too concerned about it. Everything will work out just fine. Now, I want to construct a normal plot for the pain relief data. Go to your calculators, go to Program, and you'll see an option that says Norm Plot. That's a normal plot. Select it, run the program. The data is either already stored in the list or to input the data. Well, I never use to input the data. I put the data in the list, so I'm not going to use it again later, so why input it over and over and over again? Pick a list, put it in there. Option 1, store it in the list. Which list is what this is asking for? Well, I have mine L1. That's it. Sit back and go for a ride. And this is the graph that it gives us. Now, look at this graph. If this data was perfectly normal, what we would see is every one of those dots would be right on that line. sample data is never perfectly normal. If it was, I'd be suspicious whether it was truly sample data or not, or it was contrived data. So that, to me, looks extremely normal. That looks really good. Okay, so what are we looking for in a normal plot? Well, our normal plot look like this. And again, for my students, I need you to show me the normal plot. And don't spend forever. It's not a work of art. If I look at this, and I look at my calculator, I can say, yeah, they actually did it. And that's roughly what it looks like. So what we're looking for is these data points to be very close to this line. Very close to the line. If I have something that looks like this as an example, here's my line. Maybe I'm close, and all of a sudden I come up like that. That's heavily skewed data. That is not normal. No way. So I'm looking for stuff that's very close. Now, admittedly, it's going to take a little while to get used to this. You may have to contact your professor, sit down with your professor, and say, hey, look at this one. Do you think it's normal? Yes or no, and why? It takes a little while to get a feeling for what is reasonably normal and what is not. Okay, we believe that our data is normal, so the assumptions are satisfied. The assumption, let's come back here. I'm going to write the assumption down so we have it. The assumption is that X is distributed normal. That's the assumption. It's reasonable because there's my normal plot, and it looks pretty darn good. So now I go ahead and construct a 95% confidence interval for mu. Remember, the confidence interval is always about the parameter based on the t distribution. So let's go back to the calculator. There's my normal plot. I'll second quit to get out of there, clear it off. Go to Stat, Calc. And if I go down, whoops, actually I should go to Test. And look at option 8. It's the t-interval. Select it. Again, I have data. My data is in L1. The confidence level is 0.95. Calculate it. And what I get for confidence interval is 13.734 to 17.082. And I need to correct this. This is a typo. This should be tests on your calculator. So now I'm going to say I'm 95% confident that the true average time to effective pain relief is between roughly 13.7 and 17.08 minutes. And this is based on a t interval. That's it. The difference is, think about this, the difference between a confidence interval for the mean, when you know sigma and not, is the distribution. It's either a mean distribution or a t distribution. If you know sigma, it's z. If you don't know sigma, it's t. Either way, you have to justify the assumptions. Either you have data that's normal, you know the population's normal, do a normal plot, take a look and say, yeah, it is. But what happens if we take a look at a normal plot and say, uh-oh, that's not normal? What are we going to do? Well, that's actually what we'll talk about 2 segments from now. The next segment, we'll take a look at sample size, just like we need to calculate sample sizes when we did proportions. Same thing here. I needed a method of calculating a sample size so I know how big of a sample to get. So I come back, and if I do a confidence interval, I can control that margin of error. The concept is exactly the same as what we did for proportion. It's just some of the values are a little bit different, or way we find those values is a little bit different. So once we do that, then we can say, well, suppose I look at my data, and the data is not normal. What do I do then? That would be the last segment in this series for confidence intervals.